CCD detector, when you collect some 20-30 images, you get about 100 to 200 reflections, and out of those 200 reflections, maybe about 100 reflections will have HKL general values. And then immediately we have software to look for any systematically absent set of reflections from those HKL sets. So then you will be able to predict whether it is a face-centered lattice or a C-centered lattice or something else. So at the beginning we only know whether it is a centered lattice or a primitive lattice. Based on that, we collect data. At the end of data, we extract the data in terms of HKL versus intensity, a big Excel type of file. The formula that I have given today, some time ago, gives you the total number of possible reflections, and with today's diffraction software and today's detector, you collect same reflection multiple times with different orientation of the crystal. So the HKL file that you will get may have 20-30,000 lines. Maybe 30,000 reflections have been collected, some of them are repeated, some are unique. It is not possible for anybody to physically look for those systematic absences among those some 30,000 reflections. So we again have used a soft computer program to scan every HKL set and tabulate them. Is there any set of reflections which are systematically absent in the entire list of 30,000 reflections? That then helps us to determine the space group of the crystal. So this is absolutely important. Now if your data quality is bad and some reflections which are actually going to be present, but due to some reason it is absent or it is having very low intensity and it assumes that it is absent, then this space group determination is going to be wrong. And if the space group determination is wrong, you will not be able to solve the structure because you are trying to solve the structure based on a given space group. Of course, very recently, a new version of SELEX has come which solves the structure assuming everything as P1. No matter what unit cell you give, whether it is orthorhombic, tetragonal, primitive or trigenic or whatever, it assumes initially it as P1, solves the structure and then applies the space group belonging to that point group. That's the point group which I have taken at the beginning, and then gives you best choice of space group and that. But about 1 year ago it was predetermined space group and then you take it for structure solution. So with this we will stop. Oh, okay, I wanted to show you this photo. Sorry. So what is this? This is a rotation photograph, as I promised to show. I told I will show you. It is a rotation photograph of sodium chloride crystal. See, this dark region is the shadow of the beam stop, and this is a square detector. So the direct beam is blocked, and these are spots that we have got by rotating the crystal in front of the X-ray beam in 1 minute, 360-degree rotation of the crystal. So the crystal was mounted and it is rotated about its axis 360 degree in 1 minute. What is happening? I don't know which axis is perpendicular to the beam. Some axis is maybe perpendicular to the beam, but of course some reciprocal lattice plane is in the plane of the beam, and I am measuring it somewhere here. So when I am rotating, the reciprocal lattice plane is rotated at some point or the other, some reciprocal lattice point is crossing your sphere and giving you diffraction spot. Now you see it is totally centrosymmetric. You can see all the symmetries that are present in the Ellipse cell. You see mirrors, you see fourfold axis and all that. So every set of spot is symmetrical on the other. This is a real great rotation photograph to see the symmetries present in the lattice. So if you take a rotation photograph of a crystalline material, you will get something like that. For a triclinic system, you may get large number of spots. For cubic F, sodium chloride is FCC, you will get less number of spots like this. But always, whatever you get is going to be symmetric, it will be centrosymmetric. In case of triclinic, you will only see center of inversion. Right? So we will stop at this.